All right, let me go over the calendar for this week. Okay, so this week we're going to be doing the second part of chapter 4. We're going to be moving into definite integrals. The idea here is that we're going to use the indefinite integrals that we learned, and we're going to be able to find area of a region without needing sigma notation, without using or needing the area limit definition of area. So our process will become a lot more efficient. But that also means that we can solve more complex problems as well. Okay, we're going to go through that process and also just more involved integral and antiderivative rules. Okay, we should be able to finish all of our new topic by next Monday. And then we'll have a couple of days of test review. And we're actually going to be making this into a 2-part test. So the first part is just going to be the process of working out problems by hand, using power rule, antiderivative rules, use substitution. Okay. And then we also need to become familiar with kind of the calculator type problems that we may experience on the AP exam. So more conceptual problems, problems where more similar to free response questions that you could see on the AP exam. But that also means that we have to become familiar with our graphing calculator. So we'll spend a day going over the steps that we can involve using our graphing calculator. If you have a 36 Pro, the scientific calculator, we can work around it, but it's a little bit it's more efficient if you have a graphing calculator. Okay, and also sometimes depending on the proctor, you may not be able to use the 36 Pro on the AP exam. So you want to make sure that you bring, hopefully you can have a graphing calculator to use leading up to the AP exam. So we're actually going to make this into a 2-part test. We're going to be kind of sprinkling in some practice problems with graphing calculator as we review, but our focus is just going to be getting ready for our first portion test. And then we'll have 2 days devoted to the calculator type questions, and we'll have a test that following Wednesday. Okay. After this, we basically only have 2 units remaining. Chapters 5 and 6, we're just kind of picking pieces that is needed for the AP exam, or that's part of our curriculum. So that's integrals of logs and exponential functions, and also differential equations, which we saw a little bit of. That's going to take some time, so we'll spend a unit on that. And then our final unit is area volume. So area volume, I think typically students have an easier time with that. So that'll be our final unit. And then we should be done with new material by around mid-March, about a week and a half before spring break. And then we're just going to spend the rest of the time, month and a half, just reviewing for the AP exam. Okay. It's like May 9th, the second week of May. But you know, even though we're in review mode, we're still going to have tests and quizzes. It's just that it'll be more of a cumulative perspective, and AP exam, try to make it similar to the format and getting used to that test format so that when we reach the AP exam, we feel comfortable and we kind of have an idea what to expect. Okay, any questions with the calendar so far? All right, so I encourage you guys to get your hands on a graphing calculator. I mean, there's so many variations out there, but really if you can stick with either 83 or 84 or some version of 84, TI-84 graphing calculator, if you find one, you're going to see there's a lot of different variations of them, but the ones that we're going to, the features that we're going to be using is going to show up on all the 84. So it doesn't matter what type of TI-83 or 84 that you get. It's just if you have any version of it, it'll do what it needs to do for our class. All right. Okay, so if you guys can turn to page 3. All right, so here's the packet, but we're going to look at page 3 first. I want to kind of give a general overview comparing between what we achieved first semester versus what we're moving towards second semester. Okay, so the big idea here is that first semester was all about differential calculus, which is basically derivatives, right? And derivative is just a fancy word for slope. First semester, we explored rates of change, right? We found the rate of change at a point of a graph, all right? And we know that slope is basically involving, algebraically, is kind of division, right? Change in y over change in x. If we do change in y over change in x, we get the slope, we get the rate of change of that line or of that graph. Okay. This semester is integral calculus, which is the antiderivative. It's undoing the process of derivatives. Okay. And if you think about, well, if slope is dividing two values, and if I want to undo division, I can make it multiplication, right? So if I want to undo y2 minus y1 divided by x minus x1, it will be y2 minus y1 times x2 minus x1. Okay, the order doesn't matter, but the fact is that as we do antiderivative, we're also kind of involving area formula. And if we're involving area, that can help us solve certain types of problems as we go through that process. Okay, you can recognize this x2 minus x1 times that y2 minus y1, just an area of a rectangle, right? But the important thing is that it's area related, right? We know x2 minus x1 is the width of some rectangle, y2 minus y1 is the height of some rectangle. We get that area feature to show up. Okay, so derivative, the notation that we use for derivative is d over dx. And if you see that d over dx, it kind of has that division feature to it, right? You see that dx in the denominator. So that kind of helps remind us that, okay, this is kind of slope, right? This is derivative of a function evaluated at x equals 1, gives the slope of the curve at any point on the graph. Integral, though, has more of an area notation to it. So f of x represents the height at any moment in time, and the dx represents the width. So if you think about this as height times width, that kind of resembles area that's area of a rectangle. All right, so the integral of a function over the range from point B to point C, indicated on this graph, gives the area under the curve between those points. Okay, so I want to present a big picture perspective using an example problem. Okay, and I have the key for this on the next page if you want to just follow along. Okay. So first semester was all about finding derivative, right? And using the derivative to help us evaluate the slope of a graph. So let's say we have a function that's 3x squared. Okay, 3x squared, you know, is a parabola. I didn't extend the parabola to the negative region. I'm just going to focus on this region here. So if I want to find the derivative, we know the derivative is just 6x, right? And I put the 6x graph over here. Okay, 6x is the derivative of 3x squared, right? Just go through power rule. So let me write that here. So the derivative function can find the slope of any point on the starting graph. So if I want to find, well, I know that if I want to find a point on this graph, I just have to, if I can plug 1 into the original function, right? So I plug 1 into the function, I get 3. Right? If I plug 1 in here, I get 3. But if I want to find the slope, I can use the derivative function. I know f prime of 1 is equal to 6 times 1, which is 6. So I know that the slope of this point is pretty steep, right? This is slope of 6. And I want to show you that basically, well, if this is the derivative graph, then any point on this derivative graph is going to tell me the slope of the original graph, right? That's what first semester we explore first semester, right? It's just a point on the f prime graph is going to tell us the slope of the f of x graph, right? Same thing here. You see 2 is over here at 12. So this tells us that the 12 is giving us the steepness of this original graph, right? So that's that relationship here. From f of x to f prime is slope. Now let's say we're starting from this perspective, okay? If I'm starting with 6x, I know the antiderivative of 6x will be 6x squared over 2, which is 3x squared plus c, right? So if I take the antiderivative, it'll take me back to the original problem. But along the way, it's also going to, we can also use this feature to help us find the area under this curve. Okay, so basically this 3x squared can be used to find the area of under the 6x graph. And I want to show an example of that just to kind of give us some perspective. So let's say I want to find the area of this region here from 1 to 2. Right now I created this is a nice geometric shape, so we can actually find this without the use of calculus. But I purposely did that is so that we can convince ourselves that, okay, what we know to be true is also going to be true from a calculus perspective. So if I want to find the area of this region, okay, we can say this: the integral or the antiderivative of this function can be used to find the area under this graph. So the notation that we use for this, we're going to talk about that today, is this thing called definite integrals, where we have bounds kind of closing off that space that we're working with. Okay. We can do this from a calculus perspective. We can also do this from an algebraic perspective, because right now we have a geometric shape of a trapezoid. Okay. So we have ordered pairs under the 6x graph. I want to find the area of this. We know the area is 1/2 width, height 1 plus height 2. So we know the width here. This is a width of 1, and the heights are 6 and 12. Okay. Okay, 6 plus 12 is 18. 18 divided by 2 is 9. So without the use of calculus, we know that area is 9. Okay. Now this is purposely a geometric shape, right? Imagine this graph had curves in it, then it's not going to be a geometric shape anymore. But I want to show you that this 3x squared can help us find the area of this region. Okay, and here's the big idea here. The area under the derivative graph is equal to the rise in height of the antiderivative graph. So that's the relationship here. So these two order pairs here, okay, the order pair here at 1 is 3. The order pair of this function at 2 is 12. Now that's just a coincidence that these both share the same order pair 2, 12. Okay, that's not always going to be the case. It just so happens to just to occur in this case. The change in height, right, f of 2 minus f of 1, is going to be 12 minus 3. And what's 12 minus 3 equal to? 9. So that matches what we know to be true about the area here. So again, that's the big idea here. The area under the derivative graph is equal to the rise in height of the antiderivative graph. The ordered pair of the derivative graph is going to tell us the slope of the original graph. So it kind of highlights that relationship here between derivative and integral calculus. Okay. When we find the derivative, we're able to come to a formula that will tell us the slope. But if we're dealing with antiderivatives, we're also able, not only are we able to move back to our starting point, we're also able to solve these types of problems as well. Okay. Now, if we're just dealing with lines and geometric shapes, there'll be no need for calculus. But calculus allows us to solve problems that otherwise would be difficult for algebra, right? Imagine the graph was continually changing in slope. We wouldn't be able to just say that's the slope of the graph is a number, right? But we have to have a formula for that slope, using calculus. Okay, the other big point I want to highlight is that derivative and integrals kind of undo each other. They're inverse process of each other. It's like adding 3 and subtracting 3, right? We're able to get back to our starting point or to our a way of canceling each other out. So we have first and second theorem. We'll talk about this in a lot more detail, but right now I just want to point out a few things here. The d over dx here represents the derivative. The integral notation represents the antiderivative. So if I apply a derivative and the antiderivative on top of a function, basically these two processes cancel each other out, and we're left with something that is still basically in terms of the original function. I mean, there's some leftover things that we have to worry about. We'll talk about that later. But the big idea is that derivative and integrals kind of cancel each other out. This function is largely going to remain unchanged. Okay. Same thing here. If I take the antiderivative here, and then I'm applying it to the derivative of the function, these two processes will cancel each other out, and I'm left with something that's in the form of original function f of x. Okay, so derivative and antiderivatives, they're basically inverse processes, and they're going to cancel each other out. Okay, that's a big property that we're going to explore throughout this semester. Okay, just wanted to kind of highlight that relationship between derivatives and integrals. Let's go back to page 1. Okay. So today we're talking about the first fundamental theorem of calculus, okay, which I'm going to highlight as FFT, or abbreviate as FFTC. Basically, it says that if I'm starting at a derivative level, I can take the antiderivative, and right now the only rule that we know is power rule. We'll do the antiderivative. It's going to turn itself into its antiderivative form, and then we can plug in the upper and lower bound. When we do that, we can achieve the area of a certain region. Okay, so that just highlights the fact that this is basically spelling out this, is that the area, okay, the area under the derivative graph is equal to the rise in height, or the difference in height, in the antiderivative graph. Okay. So that's really first theorem of calculus right here. Yes, this is on your page 3. I'll highlight those that. Yeah. Okay. So if you put these next to each other, that's basically what this is saying. Okay, the area under the derivative graph, let's say f of x is my derivative graph, is equal to the rise in height or the change in height of the antiderivative graph. So f of b minus f of a is the change in height. Okay. So let me kind of recap some things that we already know. The general derivative is a slope-finding function or formula. Right? That's from first semester. If I find f prime does the job of telling me the slope of the original graph. So the specific derivative is the actual slope. So once I have my formula, I can use this formula to find out any point on the original graph. If I want to find f prime of 3, I can plug that in. If I want to find the slope at 9, I can plug that in. Whatever number I get in return will be the actual slope. But the formula is it's adaptable, right? You can find any point on, you can find the slope of any point on that curve just by using that slope formula. Okay, likewise, the antiderivative, the indefinite integral, is an area finding function. Okay, we did that with going through, you saw that on the quiz where you did the antiderivative and you included plus c. Okay, what you found is not only the antiderivative, but you also were able to find the area finding formula for the original function. So the x squared plus c is the area formula for the 2x. But if I want to find the actual area where I have a physical region to look for to find the area for, I have to involve bounds. Okay, so today we're going to be involving bounds and knowing how to use bounds to help us not only come across with a formula, but actually finding an area, or at least an area-related value. Okay, if a function is continuous on the closed interval, then that function is able to be integrated across that interval or through that interval. Okay, so here is an example of that process. Okay, let's say you want to evaluate the definite interval from 1 to 4 of 3x squared plus 4x minus 1 dx. Okay, let me write a version of the first theorem above so we can kind of reference it. So let's say we start off with something that we call the f prime. Okay, f prime will turn itself into f of x. This is more of a general notation. The lowercase f just means that it's going to turn itself into uppercase f. When it converts in that process, it's basically antiderivative. But for us, our specific rule, the only rule that we know right now is power rule, okay, for integrals. We're going to learn about the other rules later, but right now we're just going to be sticking with power rule. So if I start with f prime, I can do power rule to move my way up to f of x, and then I'm going to plug in my upper and lower bound. The upper bound will always get inserted first, minus, then I plug in the lower bound. Okay, so we're going to use this formula to help us solve this, to help us set this problem up. Now, when you do a definite integral, here's the issue that a lot of students run into. We typically read from left to right, right? So if we read from left to right, the first thing you're going to see is the 1 and 4. And the tendency is that students want to work with that 1 and 4 to begin with, right? Because it feels natural, right? That's the first number I see, that's the first number I want to use. But the 1 and 4 is actually the last thing that we do, okay? We're going to have to find the indefinite integral first, go through power rule first, and once we find the antiderivative, then we work in the bounds. Okay, so it kind of works opposite from what you would expect. Okay, if we plug the 1 and 4 into this function, then we're evaluating the y values under this function, and that's not going to tell us the area of what's under this graph. Okay. So let's ignore the bounds and let's just take care of this problem first. You know that every term is set up and ready. Remember our power rule conditions. Radical has to be resolved. No variable in the denominator, no parentheses. Here we did have parentheses, but then there's nothing outside those parentheses, right? There's no exponent, there's nothing to distribute through. So when you see a bounded integral problem, just think about the fact that this is what you're going to solve first before you can even work in the bounds. Okay. All right, so let's go through this process here. Everything is set up and ready for power rule. What does 3x squared become? Okay, I'll clean that up later. 4x becomes, and the 1 becomes minus 1x. Now, typically, we would do a plus c, right? But here's the issue is that for definite integrals, I have to note here, for definite integrals, we don't need to worry about the constant of integration. It'll always wash out. So if you see bounded integrals, ignore the plus c, just don't include the plus c. It'll eventually just cancel each other out. So there's no need to worry about the plus c. Okay, good so far? Now what we've achieved is we found the antiderivative. We're sitting now at the f of x level. Okay. Let me clean this up here. Once you find the antiderivative, okay, you're not going to work in the bounds. So the way that I want you to use notation for working the bounds is use a half bracket. The half bracket indicates that I'm about to now involve the 4 and the 1. Okay, so now that we're at the function level, the upper bound gets inserted first. So whatever is up here gets inserted for all the x's in your antiderivative. Typically, we're going to see a larger number above and a lower number, or a smaller number below, but they could be a flip-flop. If they're flip-flop, just whatever number is here, just blindly plug that in. Okay, don't have to worry about, oh wait, do I need to change the bound, the order of bounds? Whatever the answer is supposed to be, it's supposed to be that way. So whatever number is sitting up here, even if it's smaller than this number, that's the first number that you enter in. Okay, that's what this rule says. Whatever is sitting in the upper bound gets inserted in first. So 4 will get inserted for all the x's. Okay, minus, now we work in the lower bound. Okay, so 1 gets inserted for all the x's. Big parentheses here. Okay, so I'm really just applying this first theorem here, right? Go through power rule, f prime turns itself into f of x, then the upper bound gets inserted. The bounds is never the first thing you do. It's always the last thing you do in your process. Now, this is going to get us down to a number. I'm going to just summarize this. This totals up to be 92. This second portion totals to be 2. And that gives us 90. And what that 90 represents is that 90 represents the area under this graph. So let's say the 3x squared plus 4x minus 1 looks something like this. From 1 to 4 is really giving us the area of that region. All right, let's look at number 2. Number 2, we're still going to also find the antiderivative first and then work in the bounds. The bounds is never going to play a role with the original term you see in front of you. So we're always going to handle this problem first. All right, is this problem ready for power rule? Yes, right? What does 2x become? Okay, once you've created your antiderivative, then you can work in the bounds. Whatever number is sitting above gets entered in first, followed by the number below. I can reduce that, make it x squared, so upper bound gets inserted first. minus the lower bound gets inserted for the x. Okay, what do we get? Okay, what's strange about that number? It's negative, right? Typically, when we think about area, we're not thinking negative, right? We can't have negative area. So this just goes to highlight that this process gives us the accumulation of change, which is area related, but it's not quite area. So we're going to have a more spelled out formula for area, which we're going to learn when we get to our area unit, area volume unit. But right now, just understand that we're going to be getting a value that is area related, but not quite area the way we define area. Yes?
So that number is basically just like the absolute value.
Sort of. Let me show you what this is really, why that's giving us a -3. Okay, let me show you what it's really giving us. Okay, so imagine you have the graph that's 2x, right? You find the region between -2 and 1 under this 2x graph. But 2x is actually going to be a linear graph that looks like this. Now, what this is doing is it's actually finding the region between the x-axis and the graph. But look at where this graph is. There are portions of it that sits below the x-axis, or below, yeah, and then portions of it that's above the x-axis. So when we talk about area, this is the region that's to the left of 0, but then this is the region that's to the right of 0. The area of this triangle is going to be 4, but then because we're accumulating negative y values, it's actually giving us -4. This is a triangle, right? It's accumulation of regions above the x-axis. It's actually going to give us a +1. So the true area is really 4 plus 1, which is 5. But for our purposes, the definite integral is going to return us -4 plus 1, which is 3, -3. So if I want to find the area, we can involve absolute value, but it's not always going to give us the true answer every time. Okay, we have a better formula for that. We'll talk about that in the next few units. Okay, so right now, when you think about definite integrals, just know that it's area related, but not quite area that we expect from area. So it's possible to have negative values come out. Okay, next page. Okay, let's go through some properties of definite integrals. Let's say I have a graph, just for visual purposes. Let's say I started at some point A. But let's say I started at A and ended at A. If I start and end at the same place, do I have a rectangle or any area to find? So there's no width, right? If I have no width, I can't have area. If I don't have area, then it's always going to be 0. So this tells us that if my bounds are the same, that means I haven't moved. If I haven't moved, there's no area to find. It's always going to be 0. Okay. All right. The second property is if I want to find the integral from a to b of f of x, that's going to be some area, right? But sometimes your a and b values may be flip-flops. Sometimes your values may be higher below than above. And sometimes it's easier for us to flip the bounds to make it either matching a property that we have or makes it easier for us to read the graph. So this is just a nice property saying that if you want to flip the bounds, feel free to flip the bounds, but just understand that when you flip the bounds, you're actually changing the value to be the negative version of what you are working with. So to maintain balance, if you ever want to sort the bounds to make the problem give you a different field or different starting point, you can do that. Just make sure that you include a negative in front to balance that value out. So if you ever want to flip the bounds, flip it and then change the sign. Otherwise, you're going to be completely changing the overall value of what you're working with. Okay, the third property says that I can basically do divide and conquer here. That's a stray mark there. That should not be, it looks like a negative there, but it should just be integral of f of x. Okay, sorry about that. Looks like there's a stray mark there. It looks like a negative. So if I have a large region from A to B, let's say I have a larger region from A to B here, I can, and if there's a point in between, I can, if the problem allows, for me to split into smaller regions. I can basically find the area of a smaller region, or two smaller regions, or multiple smaller regions, and I can just individually take care of each of them, and then I can sum them together. So if I want to find the full integral from A to B, assuming that there's a C that sits in between, I can think of this larger region as the integral from A to C plus the integral from C to B. So sometimes it's to our advantage to break a problem into smaller parts. Okay, so let's practice using those properties with example 3. First property says if the integral from 0 to 3 is 4 and the integral from 3 to 6 is -1, find the below. I just want to create a picture that could resemble these properties, just to kind of have something visual to look at. So the integral from 0 to 3 means that I can create a region above the x-axis and call it 4. But the region from 3 to 6 is going to have more parts below the x-axis than above. I'm going to call it -1. So the area is 1, but the integral is -1. I'm going to make this a little bit smaller, and I'll call this -1. Yes?
That graph, like f of x dx, that's the f prime graph, right?
Yes, you can think of this as the f prime graph, yes. Yeah. Because the result of this would be the f of x, yeah, okay. So the integral from 0 to 6 of f of x, let me just call this f of x for now. The integral from 0 to 6 will be the same thing as just totaling these up together, right? So this will be equal to what? 3, yeah. The full region will be 3 because we know we got to track our negative values as well. So if I want to write this thing fully out, I can say 0 to 3, and then from 3 to 6. Okay, so 0 to 3 has a positive region of 4. 3 to 6 is -1. Okay, part B says the definite integral from 6 to 3. Now, I don't have a property for 6 to 3, but I have a property for 3 to 6. How can I make this look like my property? Yeah, change the bounds, right? I can change the bounds, but I can maintain balance by forcing a negative outside. So I've created an equivalent expression, but I've made it so that I can match a property exactly with what I want to use. So once I flip those bounds, I have a property available for me. I know from 3 to 6, my integral is -1. I can make that substitution, but I've also made an adjustment. So I just have to work out that adjustment. So the value will be what? +1. Okay. What do you notice about part C? Bounds are the same. If the bounds are the same, your value is always what? 0. Okay. Part D is a little tricky. And the trickiness is the fact that the 3 looks like it's just the 3 standing there by itself. But the 3 is under the umbrella of the integral. So we have to understand that both these terms are being impacted by the depth integral. So to make it a little bit easier to see these parts, let's split this into individual parts, right? If I have a plus sign or minus in between, I can treat them like 2 separate problems. Okay, so these are the same things, but then this makes it easier for us to identify that, oh, I'm just solving I'm solving 2 separate problems here. And then at the end, I'll just total them up together. This first one is, we can use properties given to us. But this second one here, integral from 3 to 6 of 3 dx, can we use? Well, imagine the bounds aren't here. If I just asked you for integral of 3 dx, what would you use? Power rule, yeah, so we can use power rule for this. So 2 separate parts, 2 separate processes. Okay, we really need to treat this like individual problems. So this first one, we can use properties, right? I'm going to just highlight this integral here. What's the integral from 3 to 6? -1, so I can make that -5 times -1. We'll come back to finish off the second part, but we have to take care of this integral first, right? Ignore the bounds. The bounds are not going to play a role initially. Just look at that 3 dx. What is that 3 dx going to turn into? 3x. Once you have your antiderivative, you can create your bounds, your bracket, which indicates that you are ready to insert the bounds in. Okay, so 6 goes in for x. Upper bound always gets used first. Minus sign in between, then put in the 3. What does that give us? 9. And that's going to be the second part we're going to use. The first integral will produce 5. Second integral produces 9. 5 plus 9, 14. Okay, example 4. Okay, if the depth integral from 3 to 8 of f prime is equal to 10, and f of 8 equals 6, find f of 3. Okay, there's a reminder that the first theorem can be used as an equation solving tool to find the value of an antiderivative at a specific point. So here's what we can recall. We know that integral of f prime from a to b, f prime will turn itself into f of b minus f of a. So let's just see if we can match that up and try to build this out into an equation form. And we can kind of see where the f of 8 and f of 6, f of 8 and f of 3 can play a role in helping us solve what we need to find. So if this is my first theorem and this is my specific problem, what can I write this out as? I mashed every part up here. What does f prime turn into? Okay, but what gets inserted first though? Yeah, 8, right? So f prime will transform into f of x, and then we'll plug in our upper and lower bound. Upper bound first, minus, then the lower bound. Okay, I'm just following my first theorem here for my specific problem. Now that I have this in the equation form, I can make some substitutions, right? What can I replace this with? What's given to me? Okay, and I can replace this integral with what? 10, right? That's what they tell us, right? It's equal to 10, isn't it? Okay. F of 8, you said is 6. So making that second substitution there. And then f of 3 is what I'm looking for, so leave that as f of 3. So now we can just solve for f of 3, right? So let's find f of 3. We can just, all these are just numeric values. Okay, questions? Okay, example 5. It says the area of each region is given. Okay, so area is always going to be positive, so you're going to see all these are positive values. But with definite interval, we have to keep track of the fact that there is going to be a combination of positive and negative values, depending if they're above or below the x-axis. So this is showing an area of 2, but the definite integral of this is really what? -2. So if I want to find the definite integral, I got to keep track of the negatives. Now the area would just be 10 plus 2 plus 3, which is 15. But the definite integral is 10 minus 2 plus 3. Which is 11. Okay. Any questions? I want to see if we can just get started with page 5. We won't get very far, but you guys can go to page 5. Okay, let me just introduce this topic here. Okay, good. So this is the second part of 4.4. This is average value theorem. Average value theorem is basically the mean value theorem for integrals. Okay, so mean value theorem, we're able to guarantee a specific slope over a course of an interval. The integrals for mean value theorem, we're able to guarantee a specific height for a rectangle. Right, so here's the formula, or here's the notes here. If function f is able to be integrated on the closed interval from a to b, then the average value is given by this average value theorem. Okay. There's a height component, a width component, and there's an area component. Okay. I'll break that down in a second here. But here's the side note as well. There's always going to exist a rectangle. Okay, so there's my rectangle. Such that the area of the rectangle is the same as the area under the curve. So let's say you want to find the area under this curve. Okay, this area is going to be some number. So imagine you're able to take that shape and you're able to mold it into a rectangle that has the same area. So if I can mold this this region into a rectangle, this is the rectangle that I have, and the average height is also the average height across all these points is the same as the height of this pretend rectangle that I'm going to create. Okay. So I'm able to find that average height over the course of the interval using this average value theorem. Okay. So let me identify some of those parts for us here. F of C represents the height. The B minus A represents the width. And then the integral represents the area. I just want to show you that this is basically, it looks messy, but it's really just rearranging the area formula of a rectangle. Okay, what's the area of a rectangle? Yeah, base times height, width times height. Okay, so let me write it this way. We know that height times the width is equal to the area. If I want to solve for height, what can I do? divide by width, right? Divide by width. If I want to just solve for h, height is just area divided by the width. Okay, we know that's true. We know that's just rearranging the area formula. I got height by itself, which is what I want. Okay. Imagine if I can take that width and I can push it in front as a coefficient. If I do, it'll become 1 over width times area. Okay. And this is where my formula is coming from. The height is this f of c. The width is my b minus a. And then my area is this integral notation. Okay, we'll pick up example 1 tomorrow. Have a great day, guys.